All right, good morning, everyone. Why don't we get started? We are very happy today to have Jack Lieberson to present the short and long run effects of remote work on US housing markets. His co-authors Greg and Adam are also here. So if you want to type questions in the chat, feel free. If you want to interrupt Jack and say a question out loud, feel free to do that as well. So Jack, thanks very much and take it away.
Thank you. Thanks to David and all the organizers of the AREUEA online seminar. I look forward to taking your questions. Please feel free to interrupt me with questions or put them in the chat, and my capable co-authors will take a stab at answering them. Thanks also to all the previous commenters and referees that we've had at various times who've approved the paper a great deal. So at this point, we have observed that remote work has changed the housing market in a variety of ways over the last few years and during the pandemic. The rise of remote work, which started in the 2010s, but increased dramatically during the COVID-19 pandemic, has caused an increase in housing demand as people have home offices and people want larger spaces since they spend more time at home. It's also flattened intracity price gradients as people have moved out of CBDs and towards suburbs, lowering the relative price of housing in CBDs. And it's shifted demand across cities as people move towards areas with better amenities because they don't need to be in their jobs all the time. These changes have substantially changed costs across space and changed the average cost of housing nationally, at least in the short run. This figure here shows the path of real rents and real housing prices in the United States since January of 2020. The figure on the left is the Zillow Observed Rent Index, or ZORI, which we've adjusted for inflation. And you can see that rent increased by about 8 percentage points in real terms from 20 to 2022, with a lot of that change happening in early 2021. It looks like a one-time shift that coincides with an increase in household formation, as shown by my co-author Adam Ozimek in a recent paper. The figure on the right shows the path of real housing prices over this time, of house prices over this time, which increased by about 20% in real terms. Both of these changes, of course, occurred during a time when a lot of other stuff was going on in the economy. We're a short run change where we think the long run might be very different. It might not be surprising that short-run changes in housing demand, such as larger home offices and shifts in where people want to live, should cause a large increase in housing costs in the short run. The reason is that in the short run, housing is very inelastic. Increases in demand will naturally raise prices during a time when there was very little new home construction between the short time interval and the pandemic, which reduced the amount of building. But in the long run, as new housing supply comes online, the supply of housing will adjust to accommodate shifts in housing demand. The question we're answering in this project, or the question we're studying, is what is the long-run impact of remote work on housing costs and also on population movements? We're going to study that and how the long run differs from the short run. Was there a question? No, okay. We're going to study two particular ways that the long run, that remote work might affect housing costs and populations in the long run, both of which are inspired by the channels I discussed on the previous slide. The first channel is that remote work changes where people want to live. As housing demand shifts away from CBDs and towards other parts of the country, what we call location demand is changing. People demand housing in areas where, for example, it might be easier to build. we think that the net effect, or we're going to show using our model, that the net effect on affordability depends on the location of where remote work changes housing demand. The other channel we're going to study is what we call the housing demand channel. Sorry, location demand, and the other channel that we're going to study is called the housing demand channel. Remote work increases people's demand for housing on the intensive margin. People want bigger homes, they want home offices. And this will raise costs naturally, but the extent to which it's going to raise costs is going to depend on the overall housing elasticity in the country. We're going to formalize both of these concepts shortly, and you'll see exactly how they work in the context of our model. I'm going to give you a view of 10,000 feet about our methodology and how our model is going to work before diving into the details of the model and the results. What we're going to do is build a spatial model of the US economy that is based on our previous work from Howard and Lieberson 2021, which we're going to estimate using data from the sort of time period that housing costs rose a lot, from 2020 to 2022. It's going to be a spatial model of US counties, and we're going to assume that households demand a specific quantity of housing, and they have demand for housing in each location. Every location will have a site-specific housing supply elasticity. And what we're going to do is use the data from those years, 2020 to 2022, along with the structure of our model, to back out what we consider the fundamental shocks to housing demand, so demand for more space, and to location demand, that is demand to live in different locations. And we're going to do that using data on changes in housing costs, as well as data on population flows. Combining those with some assumptions about parameter values will tell us the changes in housing demand that occurred over this time. And those shocks are going to be identified by assuming that the housing supply was totally inelastic during this time period. In other words, it wasn't possible to build new housing, and so we can read off the shocks by looking at moments in the data. Once we've uncovered the structural shocks, we're going to calculate their long-run effects by assuming that housing supply is eventually somewhat elastic. In other words, we're going to assume that housing supply reverts back to its historical levels of elasticity. We're going to plug the shocks we uncover back into the model to calculate the long-run impacts on prices in each location. So as I said, this is the view from 10,000 feet about how our model is going to work, but of course, I'll take you through it in more detail.
Before you go on, could I ask a question?
Yes, please.
Yeah, I was just wondering if you could talk a little bit about why, maybe why you think it's reasonable to assume that the housing supply was inelastic during this 2-year period. And there was a fair amount of construction.
Yeah, I think there was a fair amount, there was construction, but it takes a while for the supply to adjust in total to the amount of changes in demand. Even if we incorporate the construction that actually occurs, the elasticity is very low relative to the long-run elasticity that will take place over something like 10 years, 20 years, 30 years. Yeah. So when we talk about the long run in this paper, we're talking about many decades. And relative to that, the short run changes were very inelastic. Does that make sense?
Yeah, so I definitely get that the elasticity is going to be lower in the short run than it is in the long run. But does your model need the elasticity to be 0, or are you just assuming a lower elasticity in the short run?
Actually, it doesn't need to be 0. No, that's a good point. We could estimate exactly the same thing by assuming, for example, that the elasticity was, it was like a fraction of the long run elasticities. So we're going to use the elasticities in Han and yeah, exactly. And the way we do it is we assume that the elasticity is 0 in the short run, but we could also say, okay, the short run elasticity is a fraction of the long run elasticity. And in fact, we do something like that when we think about the fact that those elasticities were estimated over 10 years, and we project what they would be over longer time periods. We could just as well project what they would be over shorter time periods, and do exactly the same exercise. I suspect, so we haven't actually done that, but I suspect the results are going to be very similar, because as long as the housing supply is relatively inelastic over the short run, the shocks that we estimate should be pretty close to what we estimate now.
Okay, thanks.
No, that's a great point. Thank you.
Just a real quick follow-up question.
Yes.
But you're assuming that the long run elasticities are fixed, that they aren't going to shift, that as certain cities get larger, that will impact the elasticity of that, either just because they'll run out of green space to convert, or because of endogenous changes in zoning in response to population inflows that could change over time some of these elasticities of supply.
Yes, that's right. So we're taking the Baum, Snow, and Hahn elasticities sort of as a given and adjusting them for the time interval, but we're not doing any other adjustments. You can imagine doing an adjustment, for example, for the fact that some places are going to get a higher population and therefore are going to become more inelastic, right? I think that's what you're suggesting. That would be, an interesting exercise to do. And I think it would raise housing costs overall. As I'm going to show you, people shifted their location demand and moved towards more elastic areas. If those places become more inelastic, then of course that'll raise costs. That's not something we're doing now because we're trying to take these elasticities out of the box as much as possible. But that's a great point. And that's an interesting thing to think about. Any other questions? I feel like this is a good time to pause and take questions before I dive in.
I was just curious. So it seems like with the model, you have this short term, with remote work people leaving. What happens if remote work kind of goes away and then people have to go back to it? So I'm in Reno. A lot of people from San Francisco, moved out. It's very inelastic here because there's not a lot of land available. But what if people move back to San Francisco once the city opens up and they have more amenities and they need to be more in the office, with Musk putting and stuff like that?
That's a great question. That sort of depends on exactly the way that plays out. Everything in our model scales. So if we say, okay, all the shocks are half as big, then the effects will also be half as large as we estimate. But you could imagine different scenarios. For example, you could imagine one where people move back to San Francisco, but continue to demand larger housing, right? And the results of that are going to be very different than one where people stay in Reno and leave San Francisco, but they're happy to have smaller houses because the pandemic isn't keeping them cooped up indoors. And those are the types of counterfactuals that we're going to consider at the end of our paper, where we sort of think about the future of remote work. What if it increases? What if it decreases? What if it affects demand in various ways?
Perfect, thank you. And one other thing I just wanted to add to what you were saying before in terms of inelasticity. I don't know if this factors into your model, but the whole wood shortage and wood going up, so it just makes building even harder, even without the normal inelasticity of the area, just when the prices were increasing because of other shortages.
No, that's a great point. Right. During the pandemic, there were also these supply chain issues, and people weren't working and so on. So some of those things maybe just increase the and insofar as those decrease the elasticity of housing, those would contribute to sort of that assumption you make. Any other questions?
Hey, Jack.
Yes.
Yeah, can I ask a question about that the people demanding larger houses because for the impacts from the work from home, but did you ever consider possibility of maybe repurposing or redeploying basement instead of demanding larger square footage? Because if you look at residential properties, a lot of basement are unfinished in the listings, and maybe home buyers might be thinking, well, instead of demanding larger square footage, they might just repurposing whatever is given.
Yeah, we're measuring so there are different ways we can think about an expansion of housing demand. If people repurpose their existing space, then it won't really be measured in the data as long as the square footage is sort of measured using the basement. Insofar as that's happening, we won't really be measuring it, but it also might not affect housing affordability, right? If they're just repurposing the space, which they might be doing, then it won't have as much of an effect on housing costs. The main way we think that increase in housing demand showed up in the data is an increase in household formation. People moved out from their roommates, moved out from their parents, and that's something we saw happen in 2021.
Great, thank you.
All right, I'm going to continue, but as always, feel free to keep interrupting me, and maybe I'll take another pause for questions in a few minutes. So to sort of preview the findings of our model, the long-run effects of remote work on affordability are smaller than the short-run effects, and in some cases may even be negative. So as we saw from those graphs, housing costs rose dramatically in 2020 and 2021, but that was just the short-run effect. Furthermore, these two channels cause effects in opposite directions. So let me begin with the location demand channel, which we argue will eventually cause lower housing costs. We've seen that people's demand shifts away from CBDs and more to suburbs and exurbs. What we show is that means that demand has shifted towards more elastic areas of the country, or at least areas with a higher historical housing supply elasticity. I live in California. I actually moved here during the pandemic in a very inelastic place. If, like many Californians, you moved me from California to Texas, where the housing supply is more elastic, that'll cause prices to fall by a lot in California and to rise by a little in Texas because it has an elastic housing supply. And that means that on net, national prices will fall. Overall, shifting people as demand changes from more inelastic to more elastic areas, that change in location demand will cause a decrease in housing costs. We think that the net effect of the location channel by itself is 1.8 percentage points lower than the sort of baseline, or 5.2 percentage points lower just from this channel than the short run effect. At the same time, there's this other channel, the housing demand channel, where people demand larger homes. This unambiguously raises costs, but the long run effects are smaller than the short run effects as more supply slowly comes online. And assuming that the long run elasticity sort of matches its historical levels, we calculate something like a quarter of its short run effects. That means that on net, the long run price impact of remote work will be only about 20% of its short run. Now keep in mind, when I say long run effect, I mean over many decades. And also, we're talking about the impact of remote work, putting aside questions of interest rates, and changes in regulation, which also have an effect on house prices. So this isn't an unconditional forecast for what will be happen. Rather, it's a quantification of this particular channel. We also show that the impacts are going to vary across the country. In pricier cities and those used for CPI calculation, the longer run effect might be even lower. As people move out of expensive cities and CBDs, those places are going to see decreases in housing costs that are even greater. And in fact, that's something that we've already seen to some degree, including since we wrote the paper. So it's gratifying to see some of the predictions starting to come true.
Jack?
Yes.
So your model allows for difference in the short and long run supply elasticities. And by assuming the short run is either zero or constant across markets, you can identify the demand side of the model. But then when you do the long run simulations, you're also assuming that the short run demand parameters also apply in the long run. Is that fair to say?
Yeah, that's mostly true.
And I'm sort of saying maybe that's not fair. You're allowing, short and long run differences on the supply side of the market. Maybe you should also, is it valid to assume that that's not an issue at the demand side of the market?
So there are two things. One is that we think about that question in two ways. The first is that we assume that only a fraction of people were able to go remote when they really wanted to. And that fraction is a parameter that we study and we sort of see how it changes the predictions, right? If more people are allowed to go remote in the long run, then that'll have a different impact. The second is that we think, so as I mentioned a minute ago in response to another question, that the long run impacts of remote work could change housing demand in different ways. So for example, maybe the increase in demand for space was just a short-term thing that was a result of the pandemic. And then we see how those different sorts of long-run demand counterfactuals play out and how those are different than the short run. But if you have, so those are sort of the two things we do. If you have other thoughts or suggestions about how the long-run demand patterns will be different than the short run, then obviously that would be very helpful and would be really interesting to think about.
Well, the model is sort of a derivative of the McFadden model. And it has this little quirk in it about movers and stayers. So my own intuition would say in the short run, there's lots of stayers and very few movers. And in the long run, I don't know, everybody's a mover. So that would be the parameter, maybe as you're simulating, that you adjust. Thought?
Let me get to the details of the model, and then please interrupt me again when we get to that. There's a parameter that determines what fraction of the people are movers. Then I'm curious to know whether you think that parameter captures the effect that you're thinking about.
Okay.
Okay. So to provide some motivating evidence, these two figures show how population changed and housing costs, meaning rents, changed from 2020 to 2022. The top two figures show how rents and populations changed as a function of, how populations changed as a function of population density and rents. There are a couple of things that I want you to take away from these figures. Starting in the panel in the upper left, the x-axis is population density in log scale. The y-axis is population change from 2019 to 2021. And this is a bin scatter plot. What you can see here is that population shifted towards, away from CBDs and towards not exactly the lowest population places, but places with a sort of medium population density. And this shows what a paper by Ramani and Bloom call the donut effect. People shifting away from CBDs and towards suburbs and exurbs, not necessarily towards rural areas though. The figure on the upper right shows that people shifted their demand towards, or people moved towards places that had lower rents. So there's a clear downward relationship between the Zillow average rent and population change. And to some degree, you see that same donut pattern. The bottom two panels show the relationship between rent growth and population density, or ex-ante rent. Overall, rent growth was a lot higher in areas with lower population density or lower ex-ante rents. Rent growth was small and in some cases even negative in the most expensive, most dense areas. Although, as you can see from the bin scatter plot, even in those areas, rent growth was still positive. These figures capture some of the changes in location demand that we're going to try to capture through our model. Demand shifted towards cheaper places, to some degree places with lower rents. You can see that in population, you can see that in rent changes. Figuring out exactly what the structural shocks are is going to depend on a combination of population changes and rent changes in a particular way, which I'll show you. So I'm not going to go over the whole derivation of the model. I'll just give you the introduction to sort of the setup and the key equations. But if you have any questions about the sort of guts that go into deriving these equations, please feel free to interrupt and ask me, or of course, the details are in this paper and in the 2021 JUE paper, which is we use as a starting point. It's a model with discrete locations that we're going to consider over 3 time periods. Roughly those 3 time periods are sort of pre-pandemic, then shortly after the introduction of remote work, and then the long run. We're going to have a mass of people choose a location at each time period. Then at time period 1, remote work is introduced, and we're going to allow some fraction of them to move. And as I've said, it's going to be identified by assuming that the housing supply is completely inelastic. At time 2, everyone can move, and the housing supply is at its historical level of elasticity. And we're going to, as I said, use the Baum, Snow, and Hahn elasticities, but try to project them out to infinity, essentially. We're going to allow everyone to have demand for housing quantity and housing in each location. They're going to face shocks to their housing demand and to their preferences to live in each location. And each location is going to have a site-specific supply curve for housing. So that's the structure of the model. Using this structure, we're going to derive five key equations that are going to identify the structural shocks using the data. I'm going to take you through these equations one by one, and I'm actually going to start with the long-run version of the model, where supply is not inelastic, but rather matches its historical levels of elasticity. The first equation, which I've outlined in blue, says that the change in housing demand per capita is decreasing in the change in rents, along with a elasticity of housing demand, lambda, and a shock to housing demand, epsilon. Epsilon is the shock to housing demand, and that's going to be one of the structural shocks that we're interested in. The second equation is the housing supply equation. Big H is the total quantity of housing supplied in location I. That's going to be increasing in local rents, given a local housing supply elasticity, sigma. The third equation is the location demand equation. And that says that the change in total population in location I is decreasing in the rents in location I and increasing in the location demand shock, eta. Mu here is the elasticity of location demand. Will govern how much people are sensitive to rents in a particular city. And in a few slides, I'll give you some intuition about what different values of mu mean and what values we are going to use to estimate the model. The fourth equation here just says that the total quantity of housing supplied equals the change in population plus the change in housing per capita. And the last equation here is a population adding up constraint that basically says everybody has to live somewhere. This equation is really simple, but is actually important for identifying our model. And it's what distinguishes it from purely cross-sectional models, which don't make predictions about the aggregate levels of housing costs. Since everybody has to live somewhere, there's essentially no exogenous outside option, the way you have in some sort of cross-sectional urban models. The outside option is endogenous, since everybody has to live in some city which has a housing supply elasticity. And that's what's going to allow us to make predictions about the average level of costs, instead of just making predictions about relative cross-sectional changes, the way you might have in a simpler model. Now, so this is the long run version of the model. Now I'm going to show you the short run version of the model. And there are going to be 2 important differences that I'm going to identify that are different between the short run and the long run. The first is that in the short run, only a fraction of people, phi, are allowed to move. We can think of, the Calvo ferry tapping people on the shoulder and allowing them to switch locations. We incorporate this parameter because we think that in the long run, a lot more people will eventually be able to change their families, change their jobs, and move. I got a question about this earlier, and I'm hoping this captures the sort of types of intuitions that people had about this. Yes, Luis.
Thank you, Jack. When you say they're allowed to move, that doesn't mean they have to move, right?
That doesn't mean they have to move.
move. Okay,
Exactly. If they want to. Exactly.
got it.
Exactly. The other difference, of course, is that the housing supply is totally inelastic in the short run. And as I mentioned, this is something that we haven't explored, but we can probably explore different parameter values for the short run elasticity. Model becomes really simple by assuming it's totally inelastic. Becomes very easy to solve. Okay, so those are the sort of central equations in the short run and the long run.
Jack,
Yes.
just to build on Luis's point, there's no fixed cost of moving or anything like that, right? So everyone who can move will move.
Exactly. There's no fixed cost of moving. Now, we do allow people to have a preference to keep living in a particular city, okay, which are going to work a lot like moving costs. If people have a higher preference to keep living in a city, then that means that this mu parameter is going to be smaller. And they're going to be less sensitive to changes in rents in that city. Now, we've argued in our previous paper that this mu parameter should actually be very large and in the long run. And the reason is that in the long run, we think that these sorts of moving costs or location-specific preferences are not that large relative to the benefits from moving across cities. But this mu will capture the types of intuitions you might have about people preferring to stay somewhere or people having costs of moving. And that's going to be different than phi, because phi is really about the sort of short run, are you able to move? Mu could be non-zero even in the very long run. And that's going to be a parameter where we look at different values to understand how it affects the results. So given these equations, we can do some algebra and basically back out the short run structural epsilons and etas using observed data on population changes and rent changes, given some assumptions about the elasticity, lambda, mu, and phi. Here's the derivation. You can see that both the epsilons, that is the demand, the housing demand shock, demand to live in a bigger place, and the etas, which is the location demand shock, those are both going to depend on population changes and rent changes in each location, plus the demand elasticities. Now, what we're going to do is back out the etas and the epsilons, and then plug them into the long run model. And the goal is to calculate both the location demand channel, that is the degree to which changing location demand affects overall housing costs. We're also going to try to calculate the housing demand channel, that is the degree to which demand for changing size of homes affects overall housing costs. We're going to do that nationally, and we're going to do that for each location. Let me give you some intuition about how those channels are going to work. The top equation shows the location demand channel. And you can see that the first term here is a constant, and the second term here, it's constant in eta, look, the shocks. The second term depends on the covariance between the etas and a function of the sigmas. So what does this covariance mean? Well, basically, if the covariance of eta and sigma is higher, that means that people shift their location demand towards areas where elasticities are higher, and that's going to lower prices. If that covariance is negative, then that'll raise prices as people shift their location demand towards inelastic areas. So that covariance is going to ultimately govern the amount of the location demand channel. The second term is the housing demand channel, and that's going to depend on the average housing demand nationally, how much people demand larger houses, as well as the average elasticities of housing supply and housing demand. If the average housing supply is larger, then it can accommodate the increase in housing demand more. Although this term is unambiguously positive as long as the epsilons are also positive on average. They don't depend on a covariance, they depend more on the national average. Okay, now let me talk about those elasticities, which are going to be important. And since they're important, we're going to try different values and think carefully about what they might be. The first elasticity is mu, in which I've already discussed that to some degree. That depends how much location demand is sensitive to prices in a particular location, really to rents in a particular location. The Rosen-Roback type model would have mu approaching infinity, because in the long run, if we increase rents by epsilon in a location, holding everything else constant, people are going to move out until rents are equalized across space once again. Other models that incorporate things like moving costs would have smaller values of mu. We're going to try 1.07, which we take from Shea and Moretti. We're also going to consider mu approaching infinity, which we argue is reasonable from our previous paper, and other values. The second important parameter is lambda, which governs housing demand. That says if rents go up by 1%, how much smaller homes will people demand? Cobb-Douglas type model, which is pretty typical, says lambda equals 1. We're going to use lambda equals 2/3 as our benchmark, and that's based on recent work by AREUEA et al. Third parameter is the mobile share of households, which says how many people were able to adjust their housing demand in the short run, and that determines what we sort of back out of the short run data. Based on survey evidence, we're going to try mu equals 1/2, but we're going to try other values as well. Luis, you have a question?
Thank you. Yes, Jack. Every time you say housing demand, you're talking about size, right?
Yes, intensive margin
overall
demand,
quality.
demand for size. Sorry, that's probably confusing. Yes, every time I say housing demand, I mean demand for size. Every time I mean location demand, I mean demand for living in a place. Those are two notions of demand for housing in a way, right? And it's probably confusing that I'm calling one of them housing demand and one of them location demand, but that's precisely the way that I'm using them. Yes.
Okay. And in the model, they're separate in the sense that I can stay in New York City downtown and move to a bigger place, or move to a place of the same size in the suburbs.
Exactly. We're also going to allow each location to have a housing supply elasticity. We are taking the values from Baum, Snow, and Hahn's new work, I think 2023 or 2022. Those are estimated over a 10-year period, and we're going to write a dynamic model that allows us to adjust them for the long run. But we're also just going to consider the values as given as a benchmark, and then sort of for robustness, look at the long run versions of those as well. So let me talk a little bit about the estimates that we come up with. So I showed you the equations that allow us to back out the structural shocks given the parameter values. We're going to use those parameter values and come up with estimates for location and housing demand shocks using the short run version of the model. Using the benchmark parameters, what we calculate is the average housing demand shock nationally is about 0.043. So that means that people demand about 4.3% larger housing on average. And if they were able to, if everything else were held constant in partial equilibrium, then people would also have consumed 4.3% more housing in the short run. The changes in rent and population across space tell us location demand. You remember it was a function of the rent change or it was a linear combination of the rent change and the population change. Both rent changes and population changes show us that housing demand shifted towards more elastic areas. The figure on the left is a bin scatter of rent changes versus elasticity. The figure on the right is a bin scatter of population changes versus elasticity. You can see that in both cases, the most inelastic places had lower rent and lower population growth. More elastic places had higher rent growth and higher population growth. The relationship is particularly stark for population changes, but it's also there for rent changes. For rent changes, it almost looks like there's a discontinuity, where the least elastic places have the smallest rent growth.
You know, it might be useful to display these estimated elasticities by something that's not in turn estimated, like the supply elasticity. So you display them by population, maybe you just have a list of MSAs and, you know, here's what we come up with for the, you know, largest 10, the smallest 10, something that's grounded rather than estimated. Do you understand? Yeah, along the horizontal axis or something.
So let me make, so you mean show the shocks against something that
Yes.
is not
What
estimated?
is that's right. What is the estimated demand shock?
That's a great idea. I am remiss in not including it in the presentation. It is in the paper, I believe, in the appendix. So we have a figure actually where we show a map of the shocks.
Okay.
But you're right, I should have included that here. The reason I'm showing it against the elasticities is because this is the covariance that's going to determine the sort of magnitude of the shock we estimate. And the figure should give you some sense that the covariances are positive, and so location demand is going to contribute negatively towards affordability. I guess another thing you can see from the presentation is that it's a linear combination of population changes and rent changes. And if we go a few slides ago, here you can see population changes and rent changes versus initial rents and versus density. And so it's going to be a sort of linear combination of, you know, of the two figures, where the particular combination depends on the parameter values.
I know, but it's important for readers or listeners to be able to sort of
See a map.
bounce some intuition off of this, right? Did Las Vegas get twice the demand shock or half the demand shock that New York did, or what, you know, things like that.
No, that's a great point. I'm sorry I'm not showing it to you here. I would encourage you to look at the paper where you can see that.
Okay.
I think so. I don't remember what Las Vegas was, but I think it works out basically the way you'd expect. So what? Oh, I will show you maps. I will show you maps. Of course. I'm sorry. I don't know why I'm saying I won't. I'll show them to you on the next slide. I'll show them to you on the next slide. You'll see that. I'd forgotten about that.
Sorry to interrupt.
Was there another question? Dave? Another question?
Andre raised his hand.
Oh, Andre. Yes.
Hi, Jack. Now I think that you will be talking about this given the occasion, but I would like you to specify how you take into account other factors of demand, like monetary policy or other things that affected demand during the pandemic. Thanks.
Yeah, that's a great question. Those types of factors, I think, okay, let me start with monetary policy, right? I guess let me give you a multi-part answer. Monetary policy probably has especially large impacts on house prices. In the paper, we have a whole, so let me use this as an opportunity to advertise an extension we have in the newest draft of the paper, where we extend the model to also speak about house prices. So far, we've talked mostly about rents. Changes in interest rates are going to affect prices because they'll affect the discount factor that are applied to rents. In the paper, we extend this model to talk about prices, and we consider exactly that type of scenario specifically, where Changes in interest rates will change prices directly. Another thing we do is, so monetary policy could also possibly directly affect housing demand in other ways in the long run. That's something we don't quantify since we're just focused on the effects of remote work on housing demand. it would be more of a concern for us if monetary policy affected housing demand in the short run in a way that would affect rents and population movements and thus affect the shocks that we back out of our model. Does that make sense? So if monetary policy shifted demand from San Francisco towards Las Vegas in a way, and we conflate the effects of monetary policy with the effects of remote work, then that means that our estimates of the shocks are not going to be quite right. One way we think about that is by doing a sanity check of the shocks that we come up with, by projecting them onto other measures of remote work that people have already derived, to see if the measures we come up with and the other measures of remote work are related to each other. And that's in fact what the slide on the screen here shows. We run a regression, we estimate a regression where the dependent variable is the location demand shock, and then the independent variables are the remote work feasibility measure from Dingle and Nyman, plus a measure of amenities, a measure of prices, and then we also allow remote work feasibility to vary at various distances from each location. When we run this regression, we come up with an R squared of 0.37 and F stat of 84. Clearly, our location demand shocks are measuring something related to these remote work measures. 0.37 is something we actually consider pretty high, given how crude these measures are. Now, let me show you on the map that you've been asking for, which is a map of location demand shocks by county. You can see they were negative in San Francisco and Los Angeles and Boston and New York, and they were positive in New Mexico, Utah, Southern Arizona. The map on the right shows how the location demand shocks look when we project them onto the remote work measures. And we think they look like sort of a smoothed version of the measures we come up with. So for example, if you look at Florida, there's much less variation. If you look at the Boston area, there's much less variation across counties. Probably it's a smooth version because these measures are somewhat crude and we're not picking up all of the local gradations. Does that at least partly answer your question, Andre?
Yes, I was just concerned that the metal systems that you're estimating, so basically you are studying work from home, but I was thinking that maybe they will be capturing something else than work from home, but now I think it's clear to me. Thank you.
Okay. Luis.
Yeah, so how does this, so when you presented the initial motivation, the evidence, and talked about the donut effect, I thought that people would have demands for nearby counties, and so that you would see in a map kind of the donut shape, right? A city center that sees the demand for location go down, and then the surroundings, but this seems to be suggesting otherwise, like the moves were much to far distances, right? So basically there's this donut effect, but not necessarily around the CBD where you were at, but basically going to places with lower densities, across the country.
So the difficulty of a county map is that low population counties are big and high population counties are small. If we zoom in actually towards many of the large metros, you will see a donut effect. It's just a little hard to display in these maps. Perhaps we should show maps that are a little more zoomed in. It's definitely clearest in the Northeast where the counties are smaller. I don't know if you can see, okay, let's look at the map on the left. I don't know if you can see around New York. You have New York City right here with the very negative location demand shock. And then the most positive shocks are in these outer counties surrounding New York, in these like beautiful mountain places. And the same thing is true outside of Boston. The Berkshires have these really positive demand shocks, Portland, Oregon, these types of places where people moved. You can see the sort of belt around Northeast cities of positive demand shocks.
And I guess the same, now that you point out, the same around San Francisco, right? Yeah.
Yeah, exactly. The same around San Francisco. It's a little harder to see on the West Coast because the counties are so big. You can see here, LA County is just, I mean, if we could make the, if we had smaller counties, it would be more visible. A lot of this is desert, but people moved here to Santa Barbara County away from LA County. Yeah, exactly. Or any other questions?
Yes. I'm a little concerned that there still may be some monetary policy effects. This is great work, don't get me wrong. But if you plot out just several cities, house prices, major metro areas, the differentials widen out until about, I would say, mid-2022. And then they narrow. And that's shortly after you see the Fed jacking up the Fed funds rate. And I think that the ability to tease out the monetary policy effects may take you a little bit longer because of the dynamics that are involved here. It's just a concern.
So you're thinking that monetary policy is going to affect population movements or rents?
When you have fixed interest rates, fixed 30-year mortgage rates at 2% in 2021 and early 2022, that does encourage people to jump in and lock in. So there are lock-in effects from the American fixed rate mortgage, and that could affect timing effects of when people move. And then once people lock in to those rates, they may be very reluctant to sell. So there can be some interesting dynamics that may confound some of your estimates.
That's a very interesting point. I suspect what you're saying about housing lock is particularly true right now, that interest rates are high after they were low, and so people aren't moving. We think that would be captured with that fee parameter, which says that people, can't move in the short run, whereas over very long time periods, they will be able to move. Right. I agree there's housing lock now and probably for the next few years, but over a period of 10 or 20 years, as people pay to, people build home equity, those higher interest rates shouldn't affect their mobility as much. It's interesting to think about in the interest of time. I'm gonna keep moving though. Although I should finish.
Jack,
oh, sorry. Yes. Did you have a question?
Can you produce a similar map for housing demand shocks?
Yes, we could produce.
Is there any orthogonality, or are they all really highly correlated?
They should be correlated because they're going back. They are.
By construction, they could be correlated.
Yeah, by construction, they're correlated because they're both based on rent changes. Now, the effect of population movements is going to be opposite between the two, right? But
so maybe they're not.
Yeah, so maybe they're not. No, it's a good question. It's a good question. The reason we don't have that is that the housing demand, so this is the intensive margin housing demand effect, is going to be based on this sort of average effect nationally. You can see this in the lower equation. But I think it would be really interesting to look at. I agree. Okay, so based on the model, we can calculate the location demand effect and the housing demand effect. We do it nationally, we do it in each location, and we estimate it for a variety of parameter values. The first column here shows the short run total effect on housing costs. So this is real rents. And then the next two rows show those effects for CPI cities and for expensive cities. So what we learned from the first column is that the sort of realized change in housing costs was larger nationally than in the cities where CPI is calculated, which is larger in turn than for more expensive cities. Luis, do you still have a question? I wasn't sure.
No, I think my hand.
Oh, your hand is stuck up. Okay, that's fine. The second two columns show the results of the short run version of the model. By definition, housing supply is fixed nationally in the short run, and so there's no short run location demand channel on average nationally, although it can be non-zero in particular locations. Now, in the long run, the effects are very different. So let's turn now to columns 4, 5, and 6. In the long run, we think that remote work will increase housing costs because of a combination of these two channels. Looking at column 5 in the first row, we think that the location demand channel will cause lower costs. And by now, hopefully I convinced you that the intuition for that is clear. As people shift their demand towards more elastic places, the location demand effect is negative. On the other hand, that's counteracted nationally by the housing demand effect, which is to increase housing costs. However, even though the national effect is about 0.015, so that's about 1.5 percentage points, those effects are different in different cities. For example, looking at expensive metros in the very last row, the long run effect is negative, and that's driven in large part from the negative location demand effect. As people move out of those expensive metros, those are places with an inelastic housing supply elasticity, and so those are places where housing costs are going to fall. Now, that's counteracted by the increase in demand for space to some degree, but the net effect is still negative. Looking at the middle row at CPI cities, the effects we estimate are somewhere in between. Now, I'm just showing you one slice of a table from the paper. Here we assume that the elasticity of location demand, so that is how much people care about rents in a particular city, assuming that's 1.07 as our benchmark. In the paper, we also look at mu approaching infinity, which is the sort of Rosen-Roback benchmark, and we look at other parameters which can also vary. Overall, qualitatively, the sort of differences across cities and the effects of these channels are similar. You know, when we look at CPI cities, it's always going to be lower, and the housing demand channel is always going to ameliorate some of the effect. Or sorry, the location demand channel is going to ameliorate some of the effect of the housing demand channel. As I said, so this figure shows the average long-run effects of the housing and location demand channels, looking at various values of mu, looking at various values of lambda. We think that reasonable values of lambda are somewhere between maybe 0.5 and 1. Various reasonable values of mu are sort of between 1 and infinity. Reasonable values of phi, which is the fraction of people that are allowed to move, maybe between 2.25 and 1. You can see that for each of these values, the sort of overall qualitative predictions are going to remain pretty similar, even as this point estimates are going to change. Some other parameters which we think are important are the estimates of housing supply elasticity. As our benchmark, we use the measure from Baum, Snow, and Hahn. As I mentioned, we also adjust those upwards since we think that in the very long run, the supply is going to be more elastic, and we do that using the structure of a model. But we try the effects using the benchmark measures, using the model implied measures, and various things. Okay, I already mentioned house prices briefly, and I'm just about out of time. So I won't actually show you our full dynamic model involving house prices. We think house prices are really important because ultimately many Americans buy their houses and they don't rent. I can, in the interest of time, I'll give you some intuition about why we think the results are going to be pretty similar both ways, which is that the cross-sectional changes in house prices and rents over this time were similar. Nationally, house prices rose a lot more than rents, which is partly an effect of low interest rates and mortgage policy. But the sort of relative percentage differences across cities were relatively similar, which suggests that the long run expected location demand shocks are pretty similar to the short run shocks that we estimate. We formalize this intuition using a model and compare the sort of effects on house prices in the long run and the short run to the effects on rents in the short run, and look at some of the transition dynamics. Okay, the last thing that we want to talk about is population movements. This figure shows the population change as a function of the long-run housing supply elasticities. And here we've shown it using in period one and sort of in the very long run, using different values of the housing supply elasticities. So we say t equals 1, this is the observed population change. T equals 2 is the sort of predicted change in the long run. And what you can see is that in the most inelastic places, we think population will continue to fall relative to more elastic places. And hopefully the intuition for that is clear to you from our model, which is that the more elastic places like Texas, in the short run didn't build much housing over the 2 years. In the long run, they'll build more housing. And so as people are able to work remotely, they'll move out of the inelastic places towards the elastic places. The last thing we consider is different scenarios for the future of remote work. And there are different reasons why housing demand might be different in the future than the sort of short run effects that we estimate. People might not demand homes that are as large, for example, because they are able to work in the office, even though they work remotely. People might move more as remote work becomes easier. As companies get set up for remote work, they might more people might decide to work remotely. Finally, people might shift more to higher amenity places. So the effects of amenities on location demand might be different than the short run effects. So we look at the effects sort of with housing demand, location demand, differences in amenities. We can see here, let me just draw your attention towards a few important numbers. If we increase location demand greatly, so more people are allowed to go remote, more people move, we get the results in the third section here, 700% location demand. We really increase the location demand effect. That'll make housing even more affordable because people demand housing even to an even greater extent in areas where it's elastically supplied. If we increase the demand for amenities, that'll lower prices a little bit more nationally, but a lot in the most expensive metro areas, because people are moving to areas with, nice climate and, rural Idaho, stuff like that. All right. I'm sorry for rushing a little bit at the end. I was trying to keep to 9 o'clock. But thank you all for your questions. This is the end of the presentation. I feel like I'd like to open up to other questions if people have some.
Looks like Stein has hand raised.
Thanks so much for an interesting talk. One question about prices is that if you look within metro areas, then price changes are actually slightly weaker than rent changes across space. And that's potentially interesting because that tells us potentially something about the perceived persistence of remote work. And so I was wondering whether you had thought about that and sort of how that shows up in the model.
That's very interesting. So you're saying if you look within metro areas, like across zip codes, the sort of cross-sectional
in terms of
differences in
distance from the
prices.
city center, for example.
That's very interesting. That's very interesting. So insofar as the way we estimate the model now is with counties, and we think that that's a good compromise because to some degree it's capturing differences, within a commuting zone, say. And when you look across counties, the differences across with rents and with prices are very similar. And so our model would sort of say that the long run expectations maybe across cities are similar. To really get at the effect you're looking at, we'd have to look across, I think we'd have to use narrower data across zip codes. And we don't do that mostly for data reasons, that many of our data series are not available at the zip code level. But the same
Jack, can I jump
inflation
in
from our
here?
model should hold at the zip code level, right? The CBDs are more inelastic than suburbs, within Los Angeles or something. So that would suggest that some of the effects that we expect to find are going to be weaker in the long run than in the short run if we just sort of imagined a within city version of the model. In the short run, people might have demanded moving to Orange County out of downtown LA. I guess those are different counties. They might have demanded moving towards, suburban LA out of downtown LA. In the short run, we don't expect them to. And so the location demand effect on a within city basis would be weaker.
Jack,
Greg, do you have another answer for that?
Yeah, I think that we actually do see something kind of similar in the sense that if you regress prices on rents cross-sectionally, even nationally, you get something that's slightly less than 1, I think like on the order of 0.7, 0.8 or something like that. And our model's also going to produce that, but it's not because of anything about the persistence of remote work. So even if remote work is perfectly persistent, what's going on here is that people are, in the long run, do move to further places, to places that are more elastic, and that means that the guy on the margin actually prefers is a different guy than it was in the short run. And so I'm not explaining this very well, but that generates that same sort of effect where because people are able to move in the long run, the differences in rents don't have to be as big. And so that kind of generates the dampening effect on house prices rather than rents.
I mean, that's interesting. I mean, I would have thought that sort of the marginal buyer in the suburbs is actually potentially a richer buyer because they likely come from the CBD where, house prices were a lot higher. So, I sell my Brooklyn apartment and now I can buy a much larger property in the Hudson Valley somewhere.
Yeah, sorry, I didn't mean to say it's about how rich they are. It's about how much they prefer they have their own personal idiosyncratic shock for the CBD versus the exurbs. And so as more people move to the exurbs, the marginal, the guy that's indifferent between living in both places had a lower idiosyncratic taste for that.
Any other questions? Thanks a lot. That's a really good question.
Well, if there's no other questions, I just wanted to thank Jack for an excellent presentation. You can tell by the audience participation, there's a lot of interest. So thanks again. I hope everyone here can join for our next seminar in 2 weeks, when Siddhartha Biswas from the Philly Fed will present California wildfires, property damage, and mortgage repayment. Should be another great paper. So thank you all again, and look forward to our next seminar.
Thanks a lot to everybody who asked questions, and thanks to the organizers.